So I'm going to step away from spectroscopy for a second to look at ANOVA using the Maillard reaction as an example. How we cook eggs makes a difference how they taste. Frying, which takes place at a high temperature than poaching in water, promotes Maillard reactions, but shows a wide range of taste and colour components you don't get from poaching, which is not to say that poached eggs don't have their own qualities. There's an additional question here. Why do methods of poaching eggs often suggest adding some vinegar to the poaching water? Have a think about that. We'll come back to it a little bit later on. Okay, so Maillard reactions, I'm sure we'll remember, reactions between sugars and amino acids, complex in real food. So we use in an experiment a model system to test the extent of Maillard reactions. Food's complicated, and the Maillard reaction is especially so. So in this experiment, the model system we use has glucose and egg whites. Now, glucose is just a single sugar. Egg whites are a bit more variable, and we'll see a little bit later on. The results can be quite variable. The reaction is known to produce Maillard reaction that absorb light at 420 nanometers. So that is the wavelength we measure at. Our idea, more on this in a moment, is that as we increase glucose, more Maillard reaction products are produced as measured by their absorbance at 420 nanometers. Okay, which brings us to hypothesis testing. Our basic assumption, that is our hypothesis, is that change in glucose, increase in glucose, does not influence the synthesis of Maillard reaction products in a statistically significant way. Science works like this. We don't assume what we are doing will succeed, since that may artificially influence the results. But we also have the alternative hypothesis. Change in glucose concentration does influence the synthesis of Maillard reaction products in a statistically significant ways. It's worth pointing out we must reject the null hypothesis before we can accept the alternative hypothesis. Here are some sample results presented in the way they were collected, and then paste transpose to make it easy to create the XY scatter graph and the residual plot. There's an earlier video on how to do this. It doesn't appear to be a great straight line, which is not surprising. Even blended egg white is quite variable, and there may be issues associated with how much air different samples contain. The residual plot doesn't look bad though. The points are distributed evenly above the line, suggesting it's not a bad result. So it appears on the basis of this, as we increase glucose, Maillard reactions increase. But is this increase statistically significant? It may be still just a random effect. We need to do a statistical test before we can reject the null hypothesis. Okay, so this is what statistical significance means in words. There are many mathematical ways of expressing this, which you can look up if you wish. If a result is statistically significant, that means it is unlikely to come about by random choice, and that we are probably measuring a real effect. And I put a little flowchart there at the bottom of these slides, which sort of summarizes the relationship of statistical significance and hypothesis testing. So make sure you understand that. Sorry, I've just banged the microphone. The statistical test we're using here is something called the F critical value, or the F statistic. Again, you can look this up if you feel you need to know the details, but as usual with statistics, there is a lot of detailed information which isn't necessarily what we need to know. What we need to know is how to use these statistics. The F statistic forms the basis for ANOVA, the analysis of variation between two sets of samples. As I said, it's mathematically reasonably complex, but luckily Excel's ANOVA function will do this, and I've done a video on this which I'll reference a bit later on. The function produces two values, f and f crit. We just look at the numbers. In f crit, if f is bigger than f crit, we can reject the null hypothesis and accept the alternative hypothesis. That is, we can say, at least tentatively, that our results are not the basis of random chance, but we are measuring a real effect. But we're not quite finished yet. There's another thing we need to do. And the other thing we need to do is look at the p-value. This is a measure of how confident we can be that we are measuring a real effect. It's a sort of statistical term based on probabilities. Yes, statistics, endless blather. However, if you look at these two videos, a really good straightforward introduction to statistical significance and the p-value. And the first includes some really good comments on the language to use in your reports to describe significance. We often when we see student reports, they'll say these results are significant, but what they don't tell us, do they mean statistically significant? And it's also a favourite phrase used by politicians. Such a thing is significant. Is it really? Is it statistically significant? So I recommend these two videos for understanding what the p-value means. As mentioned, Excel's ANOVA function will do this for us. It'll calculate the p-value, which is a great time saver. Often we set a significance that we want to achieve, the p-value, often 0.05. What this means is that we can be confident that if we run experiments 20 times, in 19 of them, the results will be due to some actual change we are causing rather than random effect. It's said to be statistically significant. Another way of saying this is 95% significance, or 5% significance, I beg your pardon. It would be nice to do a p-value of 0.01, 1% significance, but obviously that would be much harder to achieve. Again, there's a table there summarising the relationship to hypothesis testing. In some cases, the results may be inconclusive, but you should still report them. You should report our results, of course. Now here's the results as we obtain them from the Excel function, which I'm going to talk about where you get that from in a second. F-crit and p-value are used in combination. It's not hard to do once you've got your data. It's just a very straightforward process. So here's some example data from which is also discussed in the video. So have a look at the video, which I'm going to link, and I think on possibly the next slide. So down the bottom here we have the video which explains how to use Excel in ANOVA. In this case, our results are that F is bigger than F-crit, so we can say that we can reject the null hypothesis and accept the alternative hypothesis, and the p-value is a lot smaller than 0.05, so results provide strong evidence again to reject the null hypothesis. So see the video of how to do this. Okay, I'm going to pause here and do the and then create a final video for the final part of this little lecture.